Right, kia ora everyone. Level 2 Chemistry, 2021. Chemical Reactivity. It's generally the statement that most people rock, but I'm going to do it anyway. Okay, let's get into it. I'm just going to reformat that. Alright, calcium carbonate chips, go. All I can say off the bat for these sorts of questions is calcium carbonate seems to be used every year, or most years, so that and ethanol in structural bonding is always seems to be used. Memorize how to use this. Mainly, it always produces CO2 in acid-base reactions. Don't forget that. Why does the reaction mixture here decrease in mass as the reaction proceeds? It's a pretty quick answer. Carbon dioxide floats away as it is formed, and hence the mass goes down. Explain the changes in the rate of reaction between calcium carbonate chips and hydrochloric acid as the reaction proceeds. Refer to the graph in your answer. Now, I probably, for all these, I won't directly type out. I'm just going to explain the logic. Now, at the bottom of this, I think there is an answer schedule here. But looking at answer schedules isn't always a lot. You sort of need to know and understand. Explain the changes in rate of reaction. Okay, so this is where you have to talk about collision theory and garbage like that. Essentially, it's this exponential decay sort of curve, and the key way of saying that is at the start of the reaction there is the highest concentration of HCl and calcium carbonate, and therefore there is a much greater chance of successful collisions between reactants, and therefore the rate of reaction is at its fastest. As the reaction proceeds and time goes on, the concentrations of reactants decreases, the chance of successful collisions decreases, and hence the rate of reaction gets slower, and then you get to this sort of end point where there's no reactants left, and therefore exponential decay. That's about it generally. So let's see if I can put that into some words. So let's start. Just skip through this while we get to the next question. To the as time goes. Oh, okay. I'm just gonna see if I can get a separate answer schedule up. It's generally quite nice. Yeah. So there's a lot of yap, right? A high frequency of successful collisions. Mass decreases quickly, meaning a higher rate as the continuous amount of reaction decreases. See, this part here, they've really just said the exact same thing here. So what's really annoying about chemistry, it's just like, well, why they said this? Who knows? But whatever. This is the crux of all you need to say. Two further reactions are set up between 5 grams of this and 100 mils of hydrochloric acid as follows. Compare and contrast the two reactions. Okay, so immediately you should be thinking powder, high surface area. Okay? And if you think about it, if you have like a piece like this of calcium carbonate, it's much easier for the hydrochloric acid to attack it if it's in smaller pieces. It's much more accessible, much more exposed. And so that's what powder is. Powder is like a million tiny little pieces. So this is, again, collision theory and rate of reaction. The concentrations are the same, so that might be a good thing to say. And so this doesn't come into it. Concentration isn't a factor here. It's purely surface area. You should consider the total mass loss of each reaction. This is supposed to confuse you. both reactions use up the same amount of calcium carbonate, i.e. the mass loss is the same. Okay, that's a key thing to understand. However, the powder has a much greater surface area exposed to HCl. And therefore more successful, it's just successful collisions. Successful collisions occur per unit time. I didn't say that in the last one, so some marking schedules want you to say that. Per unit time, you know, successful collisions per second, per minute, per whatever. More successful collisions occur per unit time. Overall, the same amount of successful collisions occur in both reactions, because the same reaction occurs, but reaction 2 occurs quicker. This is the distinction between merit and excellence, right? More successful collisions occur per unit time, and therefore with powder, the rate of reaction is quicker. This is quite a short answer. I mean, they're going to just have a whole bunch of larger surface area than calcium. Powder will have more particles immediately applied, hence there will be more effective successful collisions per second. See, this is the time, right? And then they've said the same thing here, right? It will take longer to react. Well, they literally said that there. Well, they said the powder reacts faster, this reacts longer. Because both reactions will actually produce the same reduction in mass, the same amount of carbon dioxide is formed with the same amount of reaction rate used. Yep. So, okay. Yeah, see, this is another stupid thing with chemistry magazines. This and this are the exact same thing. They've just said one is quicker than the other. Oh, and now we're going to explain why this one's slower than the other. It's that comparing and contrasting, and it is a waste of time, but you do have to say it. I'm not going to bother here, but yeah, you have to say it. But they give you all the space for a reason. So you might as well do it. Here we go. Decomposition of reaction of hydrogen peroxide is a slow reaction. Yeah, I love a toothpaste. A small amount of potassium iodide. The foam produced as a result of reduction of gas. Yep. State the role. Well, you should be getting this right. It's a catalyst. Isn't used up. It just causes the reaction to occur quicker. Now, a lot of people get confused as to just why this little thing makes it so easy for this reaction to occur, and it's kind of hard to get into, but the idea is this is an ionic solid, right? And in some way, this thing is present in hydrogen peroxide, in aqueous hydrogen peroxide. It provides a surface, and when two hydrogen peroxide molecules meet on the surface, they're much more likely to react with one another. That's the idea. There'll never be a question on that, but if you're curious, that is the idea behind it. The surface sort of traps the two peroxides and they react, and it's much quicker than just leaving it by itself. Anyway, you could say that here, but it definitely won't be in the marking schedule. All they really want you to say is the Ki catalyst provides an alternate pathway with a much lower activation energy for the decomposition of peroxide to occur. Okay, that's the first part. That's what the catalyst does. It lets the reaction go bang. Remember, reactions like this may be thermodynamically favored, but if the activation energy is really high, they're just not going to happen. But what the Ki catalyst does is it makes the activation energy really low, or is negligible. It just goes, which is quite useful if you want it to work. And that's you've seen YouTube videos of this going. It just explodes. Yep. It's sort of what I was alluding to up here. It exposes / makes more available the collisions between two peroxide molecules, hence increasing rate of successful, ignore my spelling, collisions, and therefore faster / more violent / whatever reaction. Jesus, my spelling is shocking. Oh well. Alright, so lower activation energy, increase the rate of reaction. I mean, they give you a lot of space to just yap, but like, come on, it's really, you just have to say things in a really long way. Ki provides an alternative pathway with lower activation. Therefore, more reacting particles will collide with sufficient energy to overcome activation energy. That's a questionable way of putting it, but fine. Result in a higher frequency of successful collisions with often increasing rate of reaction. Yep, there you go. Increasing rate of successful collisions and therefore faster, more violent reaction. They're saying more will collide with sufficient energy. Well, the reacting particles randomly moving around have the same energy. They don't. Oh, whatever. If they want you to say that, just say it. But yeah, it's a overgeneralization. Anyway, moving on. If I do say so myself, I'll give myself a whole 8 points for that. No, never mind. Spelling error, minor error, The equilibrium constant expression for a reaction is yada yada yada. Okay, hopefully you know what Kc is trying to do. It's the ratio between products and reactants. Of course, in equilibrium, if you have an equilibrium with B, it's sort of wrong to say one is the reactant and one's the product. They're both equally but we just it's notation, right? It's just left to right. Left is reactants, right is products. But you could easily flip around and claim the other way around. But that's not the way it's typically working out. Yep, alright, so this is the products, this is the reactants. So we're saying, remember, squared means there's two lots. So it's 2 NO, yes, plus an O2, yes. And remember the double arrows is an equilibrium with 2 lots of NO2, nitrous oxide. You go. And that's it. Now if you're wondering why these things are squared, think about what happens if you were to multiply the concentration of one NO times another NO. Like if you wrote it out as A, like 2A goes to say B, the equilibrium constant is, the concentration of B divided by the concentration of A squared. But that comes from the fact that it's the same as saying A plus A goes to B. And so this is the same as saying A times A, and that's just A squared. You don't really need to know that, it doesn't really matter. There you go. Get rid of that. For the above reaction, the value for Kc at 230 degrees is 6.44. Okay, so it's like massive. I don't think this is might be part of the question, but Kc, as always said, a specific temperature. If you change the temperature, you change Kc. It's always defined at a certain temperature, and it is actually a unit in number, Kc, but it's always expressed without a unit. Like, it's never like moles per liter or whatever. But okay, so 6.44 times 10 to the 5. It's obviously massive, therefore products are heavily favoured. Like, this numerator must be massive and this denominator must be tiny to make this big number. So that tells you something about this reaction. It means that, it's pretty heavily favoured. Like, these guys here just bang, they form this. But only at 230 degrees, it's quite possible that at like room temperature, this wouldn't be so favoured. Kc might be like tiny, be less than 1. But anyway, the concentration is below, the reaction is not at equilibrium. Okay, well, you just need to find Q. Q is like Kc, but Q is an instantaneous measure. So Q would be, in this case, it's the Kc expression, and you sub the values in, so to 0.989 divided by NO 0.0102 squared and times it by 0.0128. Now I have gotten my calculator very helpfully. I'll just grab it. But the idea of this is you sub it in, right? And you should hopefully 0.0128 hopefully get something along the lines of 7426 point blah 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 blah. Look, I mean this number, the more acute among you may have noticed that it is not this number, which means the reaction cannot be at equilibrium. Because Q does not equal Kc, the reaction quotient at the moment does not equal Kc. Remember, Kc is only reached after some time. Equilibrium occurs after some time, after sufficient time for the reactants and products to have reached the same concentration. And so, yeah, so Q not being equals to Kc, it's 7,000. It needs to be 644,000. That's quite a big number. Sorry about the hiccups. But, so the reaction is going to keep going forward until Q equals Kc. So you calculate this and then you just say Q doesn't equal Kc. The reaction will continue going until it reaches equilibrium. I mean, I don't know what else I want you to say. That's about it. If only it was higher than what? Is there a squared? Oh, I've not squared my number. That's not correct. Alright, ignore everything I just said. It should be 734483. That's just fantastic. That is higher than Kc actually. So the reaction has gone too far. It's like a swing, right? It started here and it swung and then it reached equilibrium and oh no, it just kept swinging. And now it's got to go back. So it's above Kc, reaction will reverse until Q equals Kc. Yep. They don't actually refer to Q, but it's fine. Yep. I mean, it's a whole lot of full justification. I mean, Q, it's greater than Kc. Ratio of products to reactants to increase the Kc. Reactions will need to increase. Yeah, so reaction reverses. Not too bad. Oh, that's for this question. Why do they give you so much space for whatever? Justify your answer. Yeah, it's kind of stupid how much space they give you for that. Obviously, the reaction has to go backwards to reform more reactants. Because it's like overshot. It's gone too far. The following equation shows the system in equilibrium. Okay, these are always the fun questions. You've got to have a good grasp on Le Chalier's principle. I always call him Le Chandelier because it's funny, but whatever. So this is an acid dissociating in water. It's got a very low Kc value. Right, this is tiny. So what that's really telling you is this isn't a strong acid, and you should know that. Ethanoic acid is a weak acid. It doesn't really dissociate that much in water. Now, a lot of people think that means that when someone says it doesn't dissociate much, it makes these ions, and they think the reason for the saying doesn't dissociate much is because there's still this big chunk left over, and it's just an H plus proton. That's incorrect logic. What it means is in a beaker of like a bajillion of these molecules, only 0.1%, I don't know the exact number, but only 0.1% of them actually lose their proton. It doesn't like, when someone says partially dissociate, that doesn't mean like like a bit of the hydrogen falls off and it partially breaks apart. No, like you either each individual molecule either fully dissociates or does nothing. But as a complete complex, only 1% of the ethanoic acids dissociate, and so as a whole, the whole solution only partially dissociates. That's what that means. That's an important thing to distinguish. Anyway, a small concentration of concentrated ethanoic acid is added. Okay, so this is put in. Okay, you're gonna increase the concentration of the reactants. So reactant concentration increases, therefore to restore equilibrium the forward reaction is favoured to use up excess reactants and restore. So does that sort of make sense? Like you can imagine it like a seesaw. Here's my seesaw, here's my reactants, and here's my products, and they're in equilibrium. And then I just come along and I go, well, I'm going to put this big rock here, and oh no, what happens to the seesaw? It's like it's fallen over. And so to restore equilibrium, the rock puts a few of its pieces over here, and keeps a few pieces over here, and then equilibrium is restored. That's a terrible diagram, but cool. Dilute sodium hydroxide solution, NaOH, is added. Now this is a base, okay, and it's a strong base too. So this fully dissociates, and that means if you practically all of the NaOH molecules break apart into Na plus and OH minus, like all of them. It's a very, very strong base. So that's cool. So now there's just going to be this excess flood of OH minus ions. Yeah? And what that's going to do is, where are we? Yes. The excess OH minus ions that form from this will react with these hydroniums, because this is the acidic thing. Hydronium is the acidic thing. If you hadn't worked that out by now, like this is an acid, but it isn't the acidic thing in itself. This is the acidic thing. Because this thing creates hydronium, we call it an acid. Because this thing creates OH minus, we call it a base. In itself, it's not really a base. This isn't really an acid. The only acid and base is hydronium and OH minus when you really think about it. But using genuine convention, ethanoic acid is an acid and sodium hydroxide is a base. Anyway, this excess OH minus ions react with this. So let's try to put that into words. The OH ions formed by dissociation of NaOH react with the hydronium ions produced in the above reaction to form water. Hopefully you guys know that OH plus hydronium is water. To form water by removing hydronium, the concentration of the products decreases, and hence to restore equilibrium, the forward reaction is favoured to restore acid. Yep. To replace, replaces H3O, restores it. That's about it. Okay. The Kc values. Okay, this seems difficult, but you can actually do this in a really short amount of time. Okay, the temperature is increased. Okay. Here's the 4 things you need. Right, the first piece of information. the temperature of the equilibrium system is increased, the system will do whatever it can to lower temperature. Okay, that's the first thing. Okay, that's the Chalier-Tase principle. The system will always try to undo the change. The system will do whatever it can to lower the temperature. Alright, so if Kc increases, well, remember Kc is this product over reactants things, then the concentration of products must have increased. Okay? Concentration of products must have increased if Kc increases. Okay? Now, if the concentration of products increases, then the forward reaction must have been favoured. Yeah? Concentration of products increases, forward reaction must have been favoured. And so the forward reaction was favoured, and the system will do whatever it can to lower the temperature. The favoured reaction must have been endothermic to lower the surrounding temperature. Forward reaction must have been endothermic to lower the surrounding temperature, and therefore you can conclude the forward reaction is endothermic. Hopefully. Yeah. Okay. To absorb the added heat, yep, it cools the system down again. In this reaction, if Kc increases, so there will be fewer and more products. Equilibrium is favouring the products. So adding heat favours the forward reaction, hence the forward reaction is endothermic. Temperature is the only factor that can change Kc value in equilibrium. Yeah, remember that. So these sorts of questions, you just need to write down what you know and then make logical steps off it. The system will do whatever it can to lower the temperature, alright. Kc increases, the concentration of products must have increased, alright. So the forward reaction must have been favoured. So the favoured reaction must have been endothermic to lower the surrounding temperature. Because that was what? This is what bullet point 1 is saying, right? And therefore the forward reaction is endothermic. Alright, the hydrogen carbonate ion is a yada 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 yada, all that's just garbage. You can either donate a proton, you can either accept or donate a proton acting as an acid or a base. Right, as an acid, remember it's always going to donate its proton away, so it becomes CO3 2 minus. Think about this whole thing as 1 minus currently. If you lose a proton, you're going to become 2 minus. Also, you might as well remember the carbonate ion is always 2 minus. It's going to be aqueous. And water, of course, will therefore be acting as the base, and it will accept that proton in the hydronium. If it acts as a base, then it's going to take a proton, and so it must become H2CO3. There's no charge now because it was minus. So we've got a proton, it's all balanced, and OH minus. Okay, hopefully that makes sense. This one of these hydrogens went and hopped onto here, so the water acted as an acid, and this acted as a base. HCO, yeah. Is a concentration of, okay, so pH, it's on the formula sheet, I think, equals negative log times the concentration of hydronium. Now, you're not given the concentration of hydronium, but what you need to understand is that HNO3 fully dissociates. All nitrates is soluble. It just goes for it. All of these, practically all of them, dissociate into these two ions, and then these H pluses all react with water to form hydronium. Right? This reaction just happens. This reaction just happens. You never see hydronium going back into this. So they're both forward. It just bang goes for it. And so if this has a concentration of 0.0625 moles per liter, the concentration of the hydronium is actually just the same, if you think about it. Imagine there was 1 litre of water, then there would be 0.0625 moles of this, and there'd be 0.0625 moles of the H process produced, and there'd be 0.0625 moles of nitrates, and it would make 0.0625 moles of hydronium in 1 litre. And that would work no matter what your volume was. Just I've used 1 litre to make it easy. And therefore, the pH is negative log of this concentration. And that will come out to some crazy number. Negative log 0.0625, 1.2. And, you know, that should make sense. You know, it's a very strong acid. Makes logical sense. There it is, 1.2. Nice and easy. Calculate the hydroxide ion concentration of a solution of potassium hydroxide. Okay, wait, it's pH 9.5. Now, there's several different ways you can do this. The first thing is to apply the same principle. Well, you don't really need to get into it, but the first thing should be the knowledge that potassium hydroxide fully dissociates. Off it goes into K plus and OH minus in solution. It just breaks apart. Potassium and sodium are the two which just always dissociate. And so whenever you see them, you just think, bang, dissociation. So what we've got to think here is, if the pH is 9.5, well, what do we know? We know pH is negative log of hydronium. Well, that's not overly useful right now, but we can solve for hydronium. Okay, we can solve for hydronium. Hopefully you know how to rearrange this using log rules. It's 10 to the minus pH. So 10 to the minus 9.5. 10 to the minus 9.5. Now it's going to be quite a small number. 3.16 times 10 to the minus 10 moles per litre. This makes sense. There's barely any hydronium because the pH is really high. It's not acidic, it's basic. Alright, now what can we do with this? There are two ways you can do this now. First is, you have to remember this. The concentration of hydronium times the concentration of OH minus in a solution is always 10 to the minus 14. And this is sort of where the, if you think about logs being base 10 and pH being on a scale of 14, it shouldn't be too scary to see the fact that these two multiplied together give 10 to the minus 14. And armed with this knowledge, you can then say OH minus equals 10 to the minus 14 divided by the hydronium concentration. 10 to the minus 10. And that will give you, you know, some number. So 10 to the minus 14 divided by the answer. 0.00000316 moles per litre. Still not that high, but much higher than this. That's the first way of doing it. 3.16 times 10 to the minus 5. Yeah. There is another way of doing it, and it's much shorter. So I'm going to get rid of all this. That requires a lot of memory. What you can do is you can say pH is the power of hydrogen. The power of hydroxide is equal to 14 minus the pH. In other words, the power of hydroxide plus the power of pH equals 14. And that is 14 minus 9.5 equals 4.5. And then you can go OH minus equals 10 to the minus 4.5. And that will garner you the exact same answer. Yeah, 3.16 times 10 to the minus 5. Now that seems a bit confusing. I'm just going to go over that again. In the same way that pH is negative log hydronium, the power of hydroxide is negative log OH minus. Now, if you're apt with log rules, I challenge you to add pH and POH together and use the identity that H3O plus times OH minus equals 10 to the minus 14, and prove that these two must always add to 14. Yeah, right? Hydroxide. Same concentration, but different pH. So this is the, strong base, strong acid, weak base question. KLH fully dissociates, and there it is. Every single KLH molecule, pretty much, 99.9% of them go into ions. All of them, just say all of them. All of them dissociate into K plus and OH minus ions. Excellent. High. This creates a high OH minus concentration. So low hydronium concentration. Therefore, high pH. Now, using what I just taught up there, you could also say the high OH minus concentration means a very low pOH, a very low, like the pOH would be 1, yeah? And because the pOH is 1, the pH is 13, it's high. The next one is CH3NH2. Now this is a base as well because it accepts a proton. So this can react with, say, water, and it's in equilibrium, and it produces NH3 plus OH minus. And these OH minuses that are produced are what makes it basic. So this, if you take carbon, methanamine. So methanamine reacts with the water in its aqueous solution to form its conjugate acid. Now the conjugate acid actually looks like this. So CH, and then it goes to the end, and there's one H out here, one H out here, and this is sort of a bond, but it's more of just a lingering sort of thing. There's a lone pair on nitrogen which attacks this hydrogen, and that's what makes it acidic. But this will break apart when it wants to react as a base, as an acid, I mean. Anyway, so this base reacts with, in this case, an acid. Water acts as an acid to create its conjugate acid and this OH minus. Now, doesn't fully dissociate. Now, like I said, what that means is not all of these molecules in solution do this, only some do. That's why it's in equilibrium. Yeah? It's in equilibrium because, like, if there's like 10, go down to 6 of these, maybe it only produces 2 lots of this, and that's equilibrium. Maybe that's it. And so not all of them dissociated, so it only partially dissociates. Doesn't fully dissociate, but still produces some OH minus, therefore pH above 7 but below 13. Yeah, that's pretty much it, yeah? pH above 7, it's basic, it produces some OH minus ions. It's above 7, but it's less than this because it only partially dissociates. And then the last one, is this in the paper? No. The last one is methanoic acid. If you take carbon, so you'll know that. Methanoic acid. This is a weak base, weak acid, not a weak base. It's a weak acid. And so it only partially dissociates again. So you have HCOOH reacting with water. Very important is to note that this H here stays. It's just attached to the carbon, right? And this is what methanoic acid looks like. It's reacting with H2O, and it's producing HC double bond O, single bond O, and this is a negative charge. This is a base. It lost this H, not this H. Right? Okay. And so it produces this and hydronium. Producing hydronium, therefore it's acidic. So concentration of hydronium is, relatively high, and so therefore, what what did I just do? Oops. Concentration of hydronium is relatively high, therefore low pH. It doesn't fully dissociate though. So, therefore it's pH less than 7, but not like really strong, like 1. Alright. And then the electrical conductivity question. Pretty easy. Yeah, pH fits the concentration of H3O plus ions. That's a good starting sentence. That's good. Yeah. Yep, so they've got the partial dissociation, they've got this equilibrium. You see the difference between the double arrows and the single arrow. And yada yada yada. All goods. How about electrical conductivity of solutions of this and this? Alright. So good or good. All got the same concentration. So your first line should be electrical conductivity depends on free moving charge. In this case, ions. Alright. There you go. That's a good starting sentence, and now you think about it. Now, HCl, they're all the same concentration, so that's fine, that's irrelevant. HCl, strong acid, off it goes, all of them dissociate into Cl minus. So you have like your jug of water, right? And there's just H plus, which of course is just going to form hydroniums, but that's fine, that's also charged. And Cl minus, they're all just flying around wildly. Current could be passed through that quite easily. And so therefore it makes sense why that's good. I'm not going to bother writing this out because I'm running out of time. NH3, this is a base. Hopefully you know that ammonia is a base. Here it is, NH3. When you give this some water, it is in equilibrium and it makes the ammonium ion and some hydroxide. So it makes its conjugate acid, and it makes its conjugate base. Makes sense, conjugate acid, conjugate base. And that's all very well and good. It produces these guys, therefore it's a base. Doesn't really matter. The main thing is it only partially dissociates. So only some of these guys react with water. Some just, so your beaker of water will have some NH3s and some NH4 pluses. So it doesn't create as many ions as HCl, and therefore is a poor conductor. And the last one, NH4Cl aqueous. So that's the ammonium ion and the Cl minus ion. This thing goes for it, it dissociates completely. You don't really need to know that it dissociates completely. If it says good, then your argument immediately is for full dissociation, right? You don't need to guess. So it fully dissociates into these guys, lots of free moving charge, therefore good electrical conductivity. Now make sure to must have free moving charge, dissolved ions responsible for the conductivity of solutions. HCl is a strong acid and NH4Cl is a salt. They're good conductors of electricity because they completely dissociate /ionize in water, releasing the only solution. See, this is basically what I said, but in a longer, more drawn out form. That's the way you have to write it. Here's the two reactions. Make sure you always put reactions to support your argument. Ammonia is a weak base, only partially dissociates, /ionize. Only partially dissociates. Ammonia doesn't dissociate. And see, that's wrong, really, isn't it? It doesn't dissociate, it doesn't break apart, it gains another hydrogen. The ammonium ion dissociates, partly dissociates, but whatever. But it forms a lower concentration of ions, and there's the reaction there. Geez, 7, you can go chill for this, yeah, it's crazy. So that's all very well and good. Yeah, the end, generally.